Ladies and gentlemen, hello and welcome, coming to you once again, not quite live from One Take Studios. Today's topic is an introduction to properties of exponents. So we're not going to go into a ton of application today, but I would like you to see these properties and maybe just start to get a feel for them. There are going to be 7 properties that I'm going through today, depending on which list you look at. Sometimes there's 5, sometimes there's 8, but there are 7 that I am specifically looking at today. And I would like you not just to hand you the properties, but I'd like you to actually see how they work. So if you would humor me for a moment, I'm going to go through a couple examples of things and see if we can derive some sort of shortcut / model. So if I have x squared times x to the third, all right, x squared times x to the third. Think about what that means. What is x squared? What does it mean if I square an x? Well, that should mean x times x. Well, then what does x cubed mean? X cubed would have to mean x times x times x. My focus is doing really weird things today. I'm sorry. I'm hoping it's going to adjust. Maybe if I do this. Maybe. I don't know. I guess we'll see. But then we are multiplying these two things with each other. And so, what does that mean? Well, I'm multiplying 5 things together over and over and over again. That means I'm doing x to the 5th, multiplying 5 x's together. What would be then the shortcut? What would take us from here to there so that we don't have to think our way through this every single time? Well, if we look at this, this has a base of x, this has a base of x, this has a base of x. This was a 2, this was a 3, this is a 5. What did we do? Essentially, we added our exponents together. And so when we write that as a model, we write a to the m times a to the n. So please notice the similarity here. Bases are the same, bases are the same. We're putting different exponents just because we want to understand that these exponents could be different. They could be the same number if we wanted. And how does that work? We keep the base the same, so this is still a base of a, but we add the exponents together for m plus n. Ladies and gentlemen, that is our first property of the day. Know it, love it, there we go. Do these properties have names? Yes. Does anybody remember these names? Most people do not. I don't need you to memorize names, because they all kind of sound the same anyways. I need you to understand how they work, and if you can do that, I'm a happy camper. Alright, so if we can do this for multiplication, I bet you we could do this for division. That makes sense, right? What if I had, I'm going to go x to the third over x squared. X to the third over x squared. Well, again, what does this mean? This means I've got x times x, because that's what it means to cube the x, over x times x for the bottom, because x squared, again, multiplying x times x. If you go back to your grade school days of canceling, what happens here? This goes away, those cancel, this goes away, those cancel. What's left? An x. Well, let's think about it. Does this x have an exponent? Well, yeah, it does. We don't normally write it, but it would have an exponent of 1. So the question then becomes, what is the shortcut? How do I get from here to here? These both had a base of x. This still has a base of x. These were exponents, division 3, 2, 1. How does this happen? I bet you there's some sort of connection. If multiplying meant that we added, I bet you divide means that we, subtract. Ladies and gentlemen, subtraction is it. So we're going to set this up as, I'm going to have a to the m over a to the n this time. I apologize, sometimes my a stems get kind of long. They look like 9s. They're not 9s, they're a's. So a to the m over a to the n equals, well, what happens? Again, we keep the base the same, so the base is still a, but when we're dividing, m minus n. There we go. That's our new exponent. And so that is property of exponents number 2. All right, 2 down, 5 to go. You know what? I want to flip this last one over. What if I had x squared over x to the third? Because if we think about what that means, that's x squared is x times x over x to the third, that's going to be x times x times x. So, well, okay, so last time we canceled, we can still do that. That makes sense. What's left? An x. Well, I don't like the way that turned out. An x is left, but where is it? Where is it? Where is it? It's on the bottom. This was x over 1. This is 1 over x. Well, so what does that mean? What does that mean? If I use my last property, we said that if we're dividing, with the same base, we subtract the exponents. So think about that. If we were dividing, which we are, same base, x and x, 2 minus 3. What is 2 minus 3? 2 minus 3 would be x to the negative 1. So, hold on, what must that mean? When I cancel here, I've got 1x left on the bottom, and when I follow my last property, I divide, I subtract the exponents, I get a negative. What is a negative exponent? Ladies and gentlemen, a negative exponent is a reciprocal. A negative exponent is a reciprocal. The property looks something like this. If I have a to the negative n, wow, and sometimes my n's look like h's. Rawr. All right, a to the negative n is equal to, well, what's the reciprocal? 1 over a to the n. That is property number 3. There we go, property number 3. Now, I'm going to repeat something twice, and if you're smart, you'll write it down. A negative exponent is a reciprocal. A negative exponent is not a negative number. Repeat. A negative exponent is a reciprocal. A negative exponent is not a negative number. All right, you got that, right? Okay, one more that's sort of tied to these, and then I'm going to go to my next page here. I want you to think about, what does it mean if I have, let's just go with, let's just go x squared over x squared. Okay, x squared over x squared. Well, wait a minute. We know that anything divided by itself is 1. All right, we've known that for a while, right? Anytime you divide something by itself, you get 1. What does that mean for our properties? Because not that many people think about this one very often. If I track this back to our last property, we said that when we divide, we keep the base, we subtract the exponents. What's 2 minus 2? 2 minus 2 is not 2. Dramatic. 2 minus 2 is 0. A lot of people don't know why anything to the 0 power equals 1. But it's true. And so here's the model, is that anything, so a, my base of a, anything, to the 0 power equals 1. Why does this happen? Again, why does this happen? Because in order to get a 0 as an exponent, it means I had something top and bottom with the same power, and when I subtract the powers, I get 0, therefore it's going to be 1, because anything divided by itself is 1. Ladies and gents, there you go. That is why anything to the 0 power equals 1. Right there, we can see it in action, again tied back to this property right here. All right, 4 down, 3 properties to go. Dun, dun, dun. Let's see here, what else we got? There we go. All right, let's see, what's another property that we like? That would be, that bothers me. Ooh, I know, let's do this one. Okay, so next property up is going to be, if I have x cubed squared. All right, again, so all the x things I'm doing here are just things that we can think our way through so that the models actually make some sense. So again, listen to my question. What does it mean if I square x cubed? What does it mean if I square x cubed? That would mean x cubed times x cubed. Well, if I go back to this property right here, we know that if I'm multiplying with the same base, I can add the exponents. This becomes x to the 6th. So again, what's the shortcut? How do I get from here to here? Here to here, they both have a base of x, 2, 3, 6, ooh, that's multiplication, isn't it? So again, our property for this will look like a to the m to the n power, a to the m to the n, so a power being raised to a power. If a power is being raised to a power, again, we keep the base the same, but we're going to go ahead and multiply those exponents, so that is m times n. Please be careful, it is not the same as this one right here. Here we were multiplying, so we added the exponents. This is a power to a power. We are multiplying the exponents. And there we go. All right, so what else have we missed? We got that one, we got that one. Oh, let's do that one too. All right, so let's go with x, y, ooh, fancy, new variable, x, y, quantity squared. What does this mean? What does it mean if I square x, y? That means that I'm doing xy times xy. You can put parentheses there or not, whatever makes you happy, I guess. But if this is all multiplication, which it is, xy times xy, commutative property of multiplication says I can multiply these in whatever order I want, which means I could put the x's together and I could put the y's together. And lo and behold, what do I have? X squared times y squared. Ah, okay. So, again, how do I get from here to here? This is saying if I have a product, things that I'm multiplying, and I have an exponent, each of the factors gets that exponent. All right, that means that we are squaring both the x and the y, squaring the x and the y in this case, because this is a product, because we are multiplying. Okay, hold that thought because I'm going to come back to a major RAR here in a moment. So our property looks like this. We're going to go with, a times b to the m. A times b to the m. So what is this going to look like? This is going to be a to the m times b to the m. That is our property. Now, what does this look like to a lot of people? Oh, look, I distributed the exponent. Rar, no, you did not, because as soon as your brain thinks that, you get confused with the distributive property. The distributive property would be more like this, where you say, hey, look, I've got a plus or a minus. I made a big deal about this being a product. We are multiplying here. This is why this works. So people see this and they're like, oh, well, that's the same thing. I'm just going to call it x squared plus y squared. No, you are not. No. It does not work for addition. This would need to be FOILed. Multiplying? Yay, happiness and joy. The exponent applies to the x and the y, applies to both factors. Adding? No. That looks a little violent. Maybe that's because it is. I'm sorry. But when you do this for 23 years, it's nice to make progress some days. It just is. So you're going to remember that, right? You're not going to do that to me? Okay, good. Glad to hear it. Okay. One more. Ooh, it's going to look a lot like this one, though. What if we have x over y, dun, x over y, and we square that? Well, again, that's going to be x over y times x over y, because that's what it means to square something. And we all know that multiplying fractions, we all know that we multiply the top, x times x is x squared, and the bottom, y times y is y squared. So what's happening? This is an awful lot like our last one here, which makes sense because division is just the flip side of a coin for multiplication. Multiplication and division have a lot in common. And so the exponent again applies to both pieces of this. So that would look like, for a property, I'm going to do a over b to the m, which is going to be a to the m over b to the m. And again, that is going to be our last property for our list today, right there. Okay, right there. So, things that we have learned in this section right here. The exponent applies to factors. The exponent applies to our division pieces. The exponent does not apply for distributive property. We cannot do this if there's a plus here, which means we also cannot do this if this is a minus here. All right, this is bad, this is good, this is good. Ta-da! Okay, so there's our 7 properties, and if you will humor me, here's the thing. Are you listening? A lot of people see this, they're like, yeah, okay, that makes sense, I'm good, I understand it all. Yes and no. I am asking you, do not allow your brain to relax, as apparently mine has done. If your brain relaxes and you say, I've got this, I'm fine, you stop paying attention. And that is problematic. And I'm going to show you why that's problematic just by doing a couple of basic examples here. Here's going to be our first example. This is, again, based on our properties, and I'm going to call this a little mini boot camp. All right, I'm not going to show you any real applications, so to speak, as far as like the real world, but what might this look like with numbers or other letters? Dun, dun, dun. Or what happens if I've got more than one property at work at one time? This is where people start going a little bit haywire. All right, so here's what I've got for our first example, -2 times -2 cubed. And if you're not thinking, you might say, well, -2 times -2 is 4. Because -2 times -2 is 4. However, there's a 3 right there. Which property is this? Can you identify it? Which one is it? Multiplying, same base, exponent. Do you see this right here? Do you see this? This is what we have. This is to the first power. This is to the third power. what happens when I multiply? I keep the same base, negative 2, and I add the exponents. 1 plus 3 is 4. This is negative 2 to the 4th power, which is negative 2 times negative 2 times negative 2 times negative 2. Oh, come on, brain, you can do this. What is that, 16? I think that's 16. Yes, that sounds good. Ta-da! Yay, happiness and joy. It's going to be 16. Now, do I have room? I'm going to put one little example here in a different color. Actually, I'm going to put it up top here. Here's the problem that some people have, is I'm just going to go with a regular 2. I'm going to say I've got 2 to the 1st times 2 to the 3rd. And many people will say, okay, well, 2 times 2 is 4, and I add the exponents, and that's going to be 4 to the 4th. And it really bothers their mind because, well, I'm multiplying, so 2 times 2 is 4. And you know what? You're right. 2 times 2 is 4. But I want you to think about this on even a more classic level for a moment, because this is actually not going to be good for us. All right? This is not going to be good for us at all. I want you to think even more simply. I want you to think 2 to the 1st times 2 to the 1st. That's 2 times 2. Everybody knows 2 times 2 is 4. But think about this. What happens if you follow our previous logic and you say, okay, 2 times 2 is 4, and then I add the exponents, 1 plus 1 is 2, and now all of a sudden, 2 times 2 becomes 16. Last I checked, 2 times 2 is not 16. 2 times 2 is still 4. So ladies and gentlemen, when you add the exponents, you are multiplying. All right, when you add the exponents, you are multiplying. You don't get to do both. You don't get to multiply the bases together and add the exponents. You are either multiplying or you are keeping the base and adding the exponents. But through the process of adding the exponents, you are doing the multiplication. All right, so hopefully that maybe makes some sense. And if not, I apologize, but careful because that is common mistake stuff right there. Okay, next up for our example list, still sticking to numbers for the moment, I've got negative 1/3 to the negative 1st power squared. Which property does this look like? Which property? Oh. This looks like 2 properties, doesn't it? Both of these guys would come into play here. Which one do I use first? Honestly, it doesn't entirely matter. I think I'm going to start with this one. But there is no order of operations with these properties. You can use them in whatever order you would like. So I'm going to go with, I've got a power being raised to a power. So here's my base. What do? I keep my base. Oops, switch back to my blue. Keep my base of 1/3. And I multiply my exponents. So that's going to be negative 1 times 2 is negative 2. Okay, now what? Well, quite frankly, that's a negative exponent. Negative exponent. Shoot, we got 3 properties in here? Check it out. This is this, right? So what does this mean? Well, a negative exponent is a reciprocal. So that means I'm flipping this puppy over and calling it 3, because 1/3 flipped is 3 over 1, but it's still being squared. So from here to here, what have I done? The negative exponent is a reciprocal. There we go. And now, well, now 3 squared is 9. Okay, that's not bad. Wait a minute, I thought we said that we were using this property. But we kind of are. Because we're saying that we are squaring both of these, because 1 squared is 1 and 3 squared is 9. But we're also saying the negative applies to both of these. So the 1 flips to the bottom and the 3 flips to the top. Different ways that your brain can process this. You got to find one that makes sense and go with it. All right, that's going to be our final answer. But you knew that, right? Okay. All right, what if we get rid of some of the numbers and go with some of the letters? What happens here now? I'm going to ask you to pause for a moment and tell me what you think this is going to look like. With this statement, negative exponents are not allowed as part of solutions. That's part of our simplifying process. It's one of our sort of abstract rules, is we don't want to leave a negative exponent in our problem when we have it completely simplified. So please try to simplify this one right now. All right? Try it. Go. What'd you come up with? What did you come up with? Here's what a lot of people will say. Well, it's a reciprocal. So I'm going to go 1 over 2x. To the 4th, of course. Yes, but what has a negative exponent here? Does the 2 have a negative exponent? The 2 does not. This is 2 to the 1st power. This is not a package deal, so to speak. I didn't have parentheses around the 2x. They're not both to the negative 4th power. Only the x is raised to the negative fourth power. The 2 has an exponent of 1. So what does this mean? 2 does not need to be flipped over at all whatsoever. It's just a 2. But x to the negative 4, this piece is a reciprocal. So that means right now my x is on top, so to speak, and I'm going to flip it to the bottom over x to the 4th. 2, still a 2. No way to simplify that. X to the negative 4th, again, negative exponents are reciprocals. This was on top, I flip it to the bottom, and it's still x to the 4th. I can't simplify it any further. That is it. But I bet you didn't see that one coming. So again, we got to be careful with this stuff, okay? You got to think it through carefully. Don't assume that you understand, because again, as soon as you assume that you're fine, you're probably not fine. All right, one more example. Last thing today, I promise. All right, so we've got, this is, ooh, that looks like fun. 12xy over 7x to the 4th times 7x to the 5th y squared over y to the negative 3rd. This might be a lot to handle at one time. Again, my encouragement would be for you to pause and see if you can make sense out of this one. Give it a shot. What can it hurt? Go. Pause. Try it. All right. What do you think? What do you think? Let me show you where my brain goes with this, and your brain might like it or not, so you can choose. I start with the multiplication process first, because right now I could start doing some canceling things here, but if I do that, my paper is going to get really messy, and I'm concerned that I might lose something. So I'm going to think of this as the top is 12 times 7, and I'm not even going to do the 12 times the 7 multiplied out because I see a 7 here, but I've got x times x to the 5th on top, so that means I'm multiplying a grand total of 6x's together. That was this property here, and then y times y squared is y to the 3rd. Again, that's this property right here. Over, same thing, multiply fractions, multiply my denominators. I see a 7, I see an x to the 4th, and I see a y to the negative 3rd. All right. I like to stripe these in my brain, kind of stripe them saying, all right, I'm going to deal with the numbers because I know how to simplify fractions with numbers. I'm going to deal with each variable separately. So I'm going to deal with simplifying the x's, I'm going to deal with simplifying the y's and kind of go from there. All right, so what does that look like? Well, I can see 7 over 7, that's going to drop right there. That's going to leave me with 12. Okay, 12, great. And that was on top, so I think I'm just going to do a giant fraction bar here because I've got more to add to that. What will I do with my x's? Well, I am dividing, and so this property would kind of make sense. I tend to view this more along the lines of my brain sees this instead, my brain just starts canceling. I say, hey, if I cancel 4x's here with 4x's here, what's going to be left and where will it be? Well, what's going to be left? It's going to be 2x's left on top, so that's x squared, which 6 minus 4 is 2. Okay, great. What about this though? I've got y cubed over y to the negative 3. Okay, so again, multiple ways for your brain to process this. If you're looking at this guy saying, all right, that looks about right, that means I'm subtracting my exponents. I'm talking 3 minus negative 3. 3 minus negative 3 is 6. So does that really mean y to the 6th? Is that correct? Do I really have nothing left on the bottom of this? Maybe. Here's how my brain usually processes this. I see this right here has a negative exponent. And what's a negative exponent? A reciprocal. Right now this piece is on the bottom, so I'm going to flip it to the top. I already had 3 y's up here to begin with, so when I flip these 3 up to join it, I now have 6. Hey, that's actually it, guys. That's it. Simplified. All right, so do not let your guard down. Keep your eye on these guys. Keep them out while you work. Know which property you're using. Know that there could be a combination of properties, but just think, okay? That's all I'm asking you is think. No automatic pilot for your brain today. All right? Thanks, guys. Bye.